Okay, so again, my name is Omar. I'm postdoc researcher here, mainly responsible for building this mitigation controller. So please now during the presentation, feel free to interrupt me if you have some questions just on the slide that I'm presenting. So just don't wait for that. Okay, so today's presentation is about mitigation controller. The mitigation controller is a simulation tool to incorporate adaptive measures in construction projects. So usually in projects, projects are not static or dynamic, so you get delays. And then you want to try to do something about these delays to mitigate them, to reduce the time of the project. And this is done by introducing mitigation measures. But what measures you are going to choose, you need to have this optimization tool, which we are introducing today, the mitigation controller. So it helps you choose the best mitigation measures to mitigate your project. So today's presentation is going to be about the theory behind the mitigation controller. And in January, we are going to have a practical session on how to use the mitigation controller, because we have developed software for you with a friendly user interface, but it can be still handy to know what's behind it and how it works. So yeah, let's get started. So this is the outline of presentation. First, we will start with an introduction, mainly covering the basics of a project scheduling. You might already be familiar with this information, but it can be quite good for you, just like as a refreshing and to prepare you to the later topics that are covered in this presentation. And then we are going to talk about the problem, and so what's the problem that we are trying to solve, and of course how we tend to solve it. And then we are going to see the mitigation controller in which we actually implement the solution. I'm going to also show you a real life example on for the mitigation controller being applied to a real project here in the Netherlands, and I will show you also the benefits that you can get out of it. And finally, of course, we are going to conclude our presentation. So I will start with this project. This is a project which one of 5 sub-projects for the Dutch Highway Agency, Rijkswaterstaat, and that was for upgrading the road network that links Schiphol Airport, Amsterdam, and Almere over the years between 2010 2020. So you can see it's a huge project, and for a huge project, you have to have like a planning. You have to have identifying activities, and you have to have like a plans to mitigate those activities if things go wrong, and so on. Okay, so what we usually start with is a breakdown structure for any project. So you define your activities, and every activity is usually assigned with a duration. So every activity is assigned with a duration, so like a best estimate of the duration of that activity, and you list all of your activities that are going to make up the whole project. This is the first step. Second step is to do the scheduling, is to schedule the activities one after the other. So you have to specify when every activity starts and when it finishes, and when the next activity starts, and of course the relationship between this activity. So this activity must start just after that. So there's kind of dependency here. This activity can start just here. So it's kind of scheduling activity, but also identifying relationship between these activities. And finally, the duration of your project is going to be from the start of the first activity until the end of the last activity. Going back to the project that I showed you, this is how this network looks like, and we call it, of course, as you may know, Gantt chart. So we have a list of our activities listed here, and for every activity we have a duration and a starting point and end point. And we have this red colored activities. Those we call critical activities. They are critical because they are located on the critical path. And if you remember from your previous education, the critical path is a path that defines the duration of your whole project. So the duration of your project is from this point right here, the beginning of the first critical activity, until the end of the last critical activity. So in this case, usually we take special care for activities that are on the critical path, because those, if you have any delay in those activities, then your project is gonna be delayed. That's why you usually hear a lot about critical path. You have to really control that path, really control those activities, make sure that things are going as planned, more than other activities which are not critical. For example, if you look at this activity here, if instead of finishing or ending at this point right here, then it took some more time, some delay, and it finished here, then nothing will be affected after it, because as you can see here, we have something, we have flexibility here. We have something we call slack, and this gives you some flexibility for these non-critical activities. That's why we call them non-critical. So, however, all of that is based on something called deterministic approach. Deterministic approach means that every activity has a specific duration, a deterministic duration. We know when it starts, we know when it ends, and the difference between these two, a starting point and ending point, is the duration of this activity. But usually it's not the case that the activity, the duration, is going to be constant. Sometimes it takes longer than expected. Sometimes it takes shorter than expected. So you're kind of not really sure whether your activity is going to be on time. And that's why we are going to make a shift from deterministic approach, which is the one I just introduced here, to more probabilistic approach. So we are no longer going to refer to duration for activity as like constant duration, but variable duration. What that means? So every activity is going to have a distribution function for duration. So instead of assigning this most likely value for the duration to have it fixed, you can assign distribution. So your activity can take this duration here or this duration here, just randomly selected. So we give it like kind of a freedom to be randomly selected. Sometimes it's on time, sometimes it's like has delay, sometimes it's just better than expected. Okay, so every activity is going to have this probability distribution of duration, and this is the start of our probabilistic approach. Okay, now this brings me to something called Monte Carlo simulation. Monte Carlo simulation is made of several iterations of computations. So if you look at this first iteration, what we do in Monte Carlo simulation is that for every activity, we assign probability distribution for duration, and for example, activity A, activity B, and activity C, and then in every iteration, we're going to randomly select one duration. For example, we select this duration randomly, of course, for activity A, this duration for activity B, and this duration for activity C. And you know, once you know the duration of all activities, then of course you can run your Gantt chart, and then you can see the duration of your whole project. And that's 1 point. So you get one final duration for the project. And then you do that another time with another iteration. You select other durations for activities randomly, and this time here, here, and here. And at the end, you get another duration for your whole project. So if you do that like 1,000 times or more, then you get a lot of points for a lot of durations for your project. So if you draw the distribution of these durations for the project, you are going to get this kind of bell curve, the PDF. Or if you want to represent it in another way, you can also draw the cumulative curve, that's CDF. In this case, when you have the CDF, which is the distribution of a project duration, but in this case, it's no longer deterministic. It depends on something called probability. So it's not like our project is going to take like 1,000 days. No, we say it in another word. It's going to take like 1,000 days given one probability. Okay, so it's going to be conditional on the probability of your preference. And we're going to see this in the very next slide. So, and Roger here would like to give more information about that.
I just want to ask, until now, if you can all hear me, where this type of, let's say, crashing all the probabilistic is clear for you. Do you have any questions on this now? Because we assume till now that this type of information is more or less knowledgeable already for you. Is it clear for everybody? Because it goes rather quick.
So that's still basic information that I'm providing?
Basic information, and just to add maybe what is on the axis of the, because it's important.
Yeah, I'm going to show it in the very next slide, so I'm going to repeat this.
Okay, we continue.
Okay, so what I showed you here is the deterministic approach, and the step further, that's the probabilistic approach. The difference between these two is that durations are no longer constant. Okay, so that was the basic information. Now we go for the next chapter of our presentation. So what is the problem? I showed you deterministic and probabilistic approach, and this is what's used in the industry out there, right? But what is the problem? Okay, so that's quite similar to what I was saying before. So again, recap, how to estimate the project completion time. Well, we use probabilistic simulation because it is the way to go, and it's better than deterministic approach. And again, this is the same S-curve that I showed you before, so cumulative distribution of project durations. So how to use this curve again? You define your probability of your reference. In this case, for example, you would like to be 70% sure that you are going to be on time. Some companies set 80%, some of them are okay with 60%. That's totally up to them. So you go into the curve, into the S-curve, and you get the corresponding delivery time, the corresponding project time. But of course, if you select different probability, like 60%, then you are going to be to have another duration for your project, which is less, but you are less sure about it. Okay? If you want to be perfectly sure, like going with 100%, then you are sure that your project is going to be delivered with this key. Okay? So that's like kind of dependent on the probability that you want. But that's really important to mention here that projects are usually dynamic, they are not static. So things change over time, you get delay on the way. So this S-curve actually is not really constant, it's gonna move, right, day after day. What do I mean by this? Imagine that you have this project timeline from the beginning to the end. Along the way, we usually get some delays, and these delays produce kind of delay in the activities, and if your activities are delayed, then your whole project is delayed, right? But how is this reflected on this S-curve? Usually, when you get delay, then your S-curve is going to move to the right. Why? So this is the previous S-curve, but now we have delay, then it's going to move to the right, and you have the new S-curve, and that's the delayed project, but the new one, right? So for the same probability, 70% is not gonna intersect anymore at this point, but it's gonna intersect at another point because you have a new S-curve and you're gonna get a new T. And we call it here T star. That's the delayed project duration. And as you can see, T star is bigger than T, and that's why we are saying that we are having delay. All right. So yeah, things change, and then you get other S-curves. And that's it. So, but in what I showed you, and this is really what's applied in the industry out there, has fundamental error. They are using something that's not entirely correct. What do I mean by this? So this is exactly the same figure that I showed you now. So we have previous S-curve and then the delayed one, and then we have the delays, okay? But what we are modeling here, we are modeling the delays. Right, we are taking those into account, and we are getting the new curves. But do you think that a project manager will not do anything about these delays? Do you think that they are going to let the delays going on without really interfering and doing any corrective measures? It's like having no project manager, or having like this sleeping project manager that's doing nothing about it. This is the major error here, because we are not modeling the behavior of the project manager. So usually in real life, you have a delay, and then just after that, you have a human control. So you have that active guy that's trying to do something to reduce those delays, to mitigate those delays, and to try to keep the project running as planned, right? So we have these human controls. But what do I mean by human control? Is human control means trying to crash the activities, so to reduce the durations of these activities, so that your whole project is back on track, right?
So for example, if you are paving a road as part of your project, you could imagine a certain duration, and your capacity which you are allocating to this duration is, for example, 2 asphalt sets. Of course, you know, at a certain time, you know that you have maybe to crash this activity, like Omar is calling this, and basically it means you can allocate an extra set of asphalt, an extra asphalt set, sorry. So then you have 3 sets in your project available, and that means maybe that your duration from 100 can be, for example, 100 days or 100 units, whatever you are is in your time, can be reduced into 70%, for example. And so very physical thing, you add certain capacity, in this case asphalt sets, where you reduce basically in a controlled manner the activity of paving a road.
All right, so that's exactly what I was going to say, because how to crash activities, we have something called corrective measures. And as you can see here, we have like 6 corrective measures from 1 to 6. They can be something like extra resources or extra people to work or whatsoever. And these help in reducing duration of some activities. So we use corrective measures in order to crash activities. And this is the human control that we usually do to reduce it. But this kind of human control is actually not represented in the S-curve, because here it's just the delay that's represented, but we don't model what a human is actually doing in the real life. This is first fundamental error that's we want to solve, of course. But of course you can tell me that even in the industry, even out there, the project manager is not going to do nothing about it. They are going to do something. I tell you, yes, they are going to do something, but the way they do it, the way they incorporate corrective measures is also wrong, because it's already based on the wrong S-curve, which we talked about. So the way they are incorporating corrective measure is wrong, and I'm gonna prove you that this is true. So I'm gonna make like comparison here between the current approach of incorporating corrective measures, so the current wrong approach that we usually do it, and I will compare it to actual human behavior, so how a real human would behave in the same situation. And then we're gonna compare these two, and we come up with a conclusion, of course. So in the current approach, you have the S-curve that corresponds to the delayed project, because you see here it's T star. So for 70% you have T star, which is delayed, which we want to try to mitigate, right? We want to reduce. And you have a set of available corrective measures that you want to choose from. So what we usually do is that we choose a couple of them, like 1, 3, and 5, and then we run the simulation. We include them in the simulation, and we see the effect of these corrective measures. And of course, the effect is positive, so our S-curve is going to shift to the left, and our duration is going to be less. So for 70%, you are going to have T, that's less than T star, so you had the improvement. But maybe you are not happy with this T, then you try another set of mitigation measures, and we call it a mitigation strategy, in other words. So strategy 1, 3, and 4, and you get a better T in this case, but probably you are still not happy with it, then you keep trying until you get something that satisfies you. For example, here 2 and 6 will get you the best T, the T that you are looking for, that you are happy with. In this case, you stop your simulation and you consider this strategy as your permanent strategy. Okay, so what you do when you find it, that you include it in the Monte Carlo simulation, in all iteration of Monte Carlo simulation, and you do it. Okay, so but how a human would do it in the real life? Imagine that a human has like a scenario, like a project with some uncertainties and some risks. So he has like a scenario that has to deal with. He has a delay that want to try to mitigate. So he will think, okay, what is the best mitigation strategy in order to mitigate my delay? He has several corrective strategies to choose from. Then he will, of course, think by doing trial and error, and by trying different stuff, he might choose this one here, because this is the best for his scenario, which is scenario number 1. But given another scenario, scenario number 2, the same guy might choose another strategy, because this strategy now is better for this second scenario. So as you can see, it's not exactly the same scenario. So a manager is looking for this at the scenario and then deciding on the best strategy to use. And it is done by trial and error process. And also a scenario number 3 might yield another solution. So in every scenario, you might get different strategy. Okay, so this guy is trying to optimize according to their scenario. So if we look back here at this current approach, in every Monte Carlo iteration that has different conditions, we are always using the same mitigation strategy, right? But here we are using different strategies for different scenarios. And this is the key difference between the current approach of incorporating corrective measures, so always same corrective measures, and the human real adaptive behavior that's choosing different corrective strategy for different scenarios. Okay? Now, just to conclude what we said until now, we are currently employing Monte Carlo simulation in a completely wrong way, because I showed you 2 fundamental errors that we want to solve, and the correct, mainly because the correct human behavior is not integrated within the simulation, right? So we want to do something about it. So what is the solution? So how to imitate or how to model the real human behavior? Now again, I will show you the human behavior, and I will show you how we correctly model that during the Monte Carlo, during the mitigation controller. So we have scenario number 1, human chooses number 2, and how to model that correctly. So this is equivalent to Monte Carlo iteration number 1, scenario number 1, iteration number 1. And just to remind you, a Monte Carlo simulation is made up of several iterations, like several scenarios here. So in a Monte Carlo iteration, we'll choose also the second one, but we do that by means of optimization algorithm instead of trial and error process. Okay. So another scenario, first strategy, another iteration, also first strategy, a third scenario, third strategy, third iteration, third strategy. So we are trying to do exactly the same thing as a human is doing, but we are doing that with optimization and not trial and error process. We are still improving the human behavior as well. So now when you have all of these results, and then you can get the correct S-curve, because we said the previous S-curve is wrong. Now we got the correct S-curve that has human behavior inside it. This is what we want to get at the end, right? So this is how we solve the problem. Actually, we incorporated this idea inside this mitigation controller. So I'm gonna talk a bit about the mitigation controller. Don't worry, nothing in depth, and we are going to see more practical in the practical session how to use a mitigation controller. So we're not gonna talk about math here. So of course we want the tool to reflect the goal-oriented human action. We want to incorporate optimization and automation, and we want to have also ability to model risk and uncertainties. These are our needs that we cover in the mitigation controller. So just I'm not, of course, not gonna talk math here, but just the idea behind the mitigation controller is, you know, that project is made up of several paths, and we have, of course, the critical path here. So, and we have target duration. So we want to reduce the duration of our project to duration that's before the target duration, yeah, to something that's lower than the target duration. How to do that is to reduce the duration of every path to somewhere just right here. So these blue dots should be somewhere right here before the target duration, but not too far from it. Okay, because otherwise you are going to pay extra money to get that. So we apply corrective measures so that the durations are reduced. And of course we have optimization behind it that you don't have to worry about it. Now I will give you just real life example on a real application of mitigation controller back to our this project that we talked about. And here the activities that are part of this project. Actually these activities are just part of the whole project, so it's just sub-project that we are dealing with here. And our, of course, our schedule, our Gantt chart that I showed you before, all activities are scheduled as follow. Now, this is something important for you because, and we are going to talk about in the practical session, you are going to provide information for a project, like project description, starting date, end date for every activity, And of course, in this case, because we are doing probabilistic stuff, then you have to provide like 3 different values for your activity's duration. So it's not only my activity is going to take like 920 days, but also you have to provide optimistic value and pessimistic values, because they are going to be used by the software, and the activities that are dependent on these activities, so predecessors. You are also going to provide mitigation description for your mitigation measures. Just to give you example here, like extra engineering design office personnel, and this is one way to mitigate the activity. Okay. Also, these measures have like several value for capacity. For example, this measure here can contribute in reducing 52 days for activity number 3, but can also contribute, it can also reduce by 51 days. So there is uncertainty here. We are not sure, provide 3 values, and also the cost of these measures. I'm gonna talk more details in the practical session, so don't worry about that. But there's some information that you will have to provide in Excel sheet, and also a list of risk event that can also affect the duration of your activities. That's extra delay source, let's say. And I will also explain that in the practical session. So these are the information that you will need to care about, just that. Okay, do you want to add something, Roger?
No, go on for the time.
Okay, so we provided all the input, and now we run our mitigation controller, and we get this is the kind of output, the kind of main output that we get from the mitigation controller. So the mitigation controller is gonna give you 3 different S-curves. The first S-curve that's right here. That's the S-curve that corresponds to not applying any corrective measures at all. So that's when you execute your project without any corrective measures. And of course, this has has delay. Of course, this is representative to your delayed project. But also, it's gonna provide you with additional 2 curves, this dotted one and this black one. So this dotted one is represent the current approach. It's like when you incorporate all of your corrective measures at all without doing any optimization. So you have 10 corrective measures, you put all of them, and you apply all of them without optimization. You get this curve. And of course, the black one that corresponds to the mitigation controller. So as you can see, this curve is a bit slim. Okay, it's more close to. And by the way, this line here is our target duration. So this is our target duration, in this case, 1,466 days. This is some input that we give. And the mitigation control curve is very close to that one. So between these 2 curves, the dotted one and the black one, you see some gray area. So what is this gray area? Is cost benefit that you gain if you use the mitigation controller. So this is kind of representative of how much cost, of how much unnecessary corrective measures that you are applying if you don't use the mitigation controller. So we are going to save this much. Okay, I'm going to show you also how much cost we are actually saving if we use the mitigation controller just after that. But mainly this is the information that you need to pick up here. That mitigation controller is gonna reduce your cost. Is gonna tell you which are the corrective measures that you don't have to use. Okay. Okay. So if we want to,
you could zoom in on the design point only.
Okay.
By introducing that word also, that term.
All right. So we have some, as you can see here, both curves intersect at some point, and we call that point design point. Why design point? Because it corresponds to our target duration, to our input, to the duration that we would like to reach. And both curves intersect in this point. Then since they intersect, you might tell me that, well, they intersect, then they might be equally good, because at the same time, we are getting the same probability. But that's partly true because even if you go if you go with the mitigation controller, then you are not using the same amount of corrective measures. You are getting the same result, same probability, but you are using many fewer corrective measures, and this is actually translated in terms of cost. So this design point the two curves intersect, but you are using less corrective measures, and this is translated into cost. Okay? And if we want to look at the actual cost reduction, then just in short, without going in details, if you use a mitigation controller, then you are paying 1.72 million euros, in our case, of course. If you are not using a mitigation controller, you are paying 4.46 million euros, and that's a reduction of 62% of cost. That's really huge, just by using the mitigation controller, by making things more optimized. So that proves to you that the mitigation controller is quite effective, and of course you are going to see that in your own implementation later on. So of course that's not the only result that the mitigation controller gives. The mitigation controller also gives some kind of path ranking and activity ranking, which are the more critical activities, mitigation measures ranking, and so on. And these we are going to talk about later in the practical session. So we're not going to see anything about them now. But the idea here is that you are going to get additional results. All of them ready to use, of course. You don't have to write anything. Yeah.
Can you tell some words about path ranking? Qualitatively?
Yeah, of course. I can also show you a slide about path ranking. Okay, because you know when you are using probabilistic approach, the duration of activities are not constant and they change in every iteration. One iteration activity takes 100 days, another iteration 95 because there is uncertainty. And changing the duration of activities can affect the critical path because in some iteration one path can be critical path, but in other iteration another path can be the critical path because duration are changing. So you cannot really expect which one of them is a critical one. Okay, so for example, just to show you here in our example, okay, in our example, we can see for path number 2 was critical in 20% of time, path number 5 in 46% of time. So it's not like one path that's always critical. And that's something we're going to talk more about later. And that's a really interesting result. So the idea here is that you cannot really focus on one path in your project because there might be several critical paths or potential critical path when you adopt the probabilistic approach.
So does that mean that one of these paths is the critical path, right? Do you know which one by instance?
Actually, if you are looking at deterministic approach, then you are going to only have one critical path. But once you are using probabilistic approach, there is nothing called critical path, but a set of potential critical paths. In this case, 2, 5, 11, and 15. And these are the only ones. But you have to consider all of them. You cannot focus only on one of them, like the most critical in this case. And something that's really interesting, if you do deterministic study, then it's number 15, path number 15, that is the critical path. But when you are doing probabilistic, then it's number 5. So see, then deterministic approach is misleading in this case.
There is no such thing as the critical path.
Mm-hmm. Yeah, that's true. Okay, and now we can conclude our work. The mitigation controller, optimization tool to select the most effective mitigation strategy in construction project, incorporating the human, and this is important, the human goal-oriented behavior. Why it's nice? Because we have flexibility to introduce duration uncertainties, capacity uncertainties of the corrective measures, cost uncertainty, risk consideration, risk impact uncertainty, and also it's user-friendly, and you're going to see that. So yeah, of course, that was kind of theoretical background, what's behind mitigation controller. We are going to share with you this presentation, and of course, this session is recorded if you want to refer to it, and more practical information is going to be delivered at a later stage. Thank you so much. If you have any question, we can answer that.